Next, the standard enthalpy changes of neutralization for 3 acids and 3 alkalis are given below. Look at the first one. Strong acid neutralized with a strong base. Negative 57.3 kJ per mole of water formed. Weak acid neutralized with NaOH. Smaller amount of energy is released. Weak acid neutralized with a strong base. Smaller amount of energy is released. Strong acid neutralized with a weak base. Smaller amount of energy is released. Similarly for the last one. So, using the above data, answer the following questions. Which is the weakest acid? Weakest. Can you tell me which one? Which is the weakest alkali? Okay. So, weakest acid. There are 3 acids. Obviously, the answer is not HCl, HCOOH, or this one. Now, look at the data. Okay. The magnitude of the neutralization between this acid and this acid is the smallest. Therefore, this one is the weakest acid. Similarly, for base, we have NaOH, we have ammonia, and we have this one. Okay, and the magnitude, which one has the smallest magnitude? This one. 52.2, because the magnitude of the standard enthalpy change of neutralization is the smallest. Therefore, ammonia is the weakest alkali. Do you understand? Estimate the delta H for neutralization between the weakest acid, that is the weakest acid, and the weakest alkali. Okay, must be smaller than 49.9. Must be smaller. Okay, with the smallest magnitude. And then now, how to solve this problem? First of all, look at the first number and the third number. Okay, the difference between these two numbers can be used to calculate the energy required for the dissociation of this weak acid. Okay, how? The delta H, or the energy required for the complete ionization of this acid. Now bear in mind, it must have a positive sign. Okay, is equal to 49.9 minus 57.3, which is plus 7.4 kilojoule per mole. Next, compare again the first number with the fifth number. By comparing these two numbers, we can work out the energy required for the complete ionization of ammonia. You should use the first one and the fourth one. Okay, how to work this out, which is equal to The fourth one, negative 52.2 minus negative 57.3, which is 5.1 kilojoule per mole. Okay, in other words, the standard enthalpy change for the neutralization between this weak acid and this weak base, the weakest base, should be equal to, this is the situation without ionization, and part of the energy, 7.4 kilojoule, is used for the complete ionizations of the weak acid, and 5.1 kilojoule of energy is required for complete ionizations of ammonia. Therefore, the number should be 44.8 kilojoule per mole. Understand? It is difficult, okay?